This conference will now be recorded.
Hi, welcome to another OCP Top session. This is the one last session before the 2022 Global Summit happening next week in San Jose Convention Center. I'm sure that I will be seeing a lot of you. We, TAP team, prepared a packed day. It's going to be the last day of the show, so the show will run 18, 19, and 20 of October next week. And on Thursday, which is the last day, we will have our top track day. All this time, we will also have our demo center, the OCP demo center, hosting a live and static demos of the different technologies that we've been working together as a collective with all the famous and known familiar faces coming. So we are also excited to have you there, and I hope that we'll get to see everyone. I'll paste the link here so you could make sure to register. And without further ado, I will ask my colleague Lasse to tell us what we're going to do today.
Yeah, for sure. So today we're going to hear from Guy Buesnel on resilient PNT standards for data centers. And Guy is an expert in GNSS security and resilience and works as a specialist PNT Security Technologist at Spirent. Guy has a Bachelor of Science Honours degree in Physics and Atmospheric Physics from the University of Wales in Aberystwyth. And he also holds a master's degree in communications engineering from the University of Birmingham. And here comes a very impressive list. Guy is now a chartered physicist. He's a member of the Institute of Physics. He's a fellow of the Royal Institute of Navigation, and he serves on the International Advisory Council of the Resilient Navigation and Timing Foundation. In short, Guy is a bona fide expert in his field. Over to you, Guy.
Okay, thank you very much. Can everyone hear me and see the slides okay? I'm taking that as a yes. Okay.
I can, yeah, certainly.
Great. Well, what I'm going to do today, thank you very much for that excellent introduction, Lasse, and it's a pleasure for me to be here talking to you all today. I'm going to talk about why resilient PNT standards for data centers would be desirable. I'm going to really concentrate, as my speciality, on issues around GNSS and satellite navigation, which is why the need for resilient PNT standards is so important. What I'm going to do is tell you, be vulnerable, some of the complexities around taking precise time or precision time from GNSS signals. I'm not going to sort of prescribe any standards to you tonight, but what I would say to everyone on this call, if you're not familiar with it, is that there's a lot of work going on at the moment with the IEEE, who are working on this P1952 standard, which is about resilient positioning, navigation, and timing user equipment, and there were working groups in progress there. And I think that would be if you're thinking about having or looking at how a standard might affect or how could be produced or worked up that applied for your use case in data centers, then I'd absolutely recommend joining up and actually participating in this international standard, because I think there's a lot of opportunity there. But I'm going to talk tonight about some of the issues around GNSS and why these standards are important. Just looking at the vulnerabilities of GNSS, that it's a great signal. It's become ubiquitous, and it's a very cheap and effective way of getting precision navigation and timing data. But the trouble is with GNSS, the satellites are in medium Earth orbit, and the power of the transmissions, is really low. It's the equivalent of something like a 20-watt light bulb out there in medium Earth orbit. So, if you're designing a receiver to pick up GNSS signals, you have to do some very special things to recover that low signal power and the messages inside that signal as well. And because of that, it means it's vulnerable to some specific mechanisms that can cause disruption. And they're often disruptions that are related to the radio frequency signals. Because they're so low power, they're easy to disrupt. So we could start off with multipath, which is reflections from multiple sources, which we'll talk about a bit later on. And we can talk about cyber attacks. Those aren't really the main deliberate vulnerabilities. We'll get onto those in a minute. And we've got atmosphere as well, scintillation, solar activity. And if you like, the multipath and atmosphere are things that you have to deal with in any case. Cyber attacks is a non-RF mechanism, but the three that we're most used to dealing with, I'd say on a day-to-day basis with GNSS, are segment errors, which we were told when the satellites were launched, we wouldn't see segment errors, but in fact, all of the major constellations have had segment errors and issues. And also, the interface control documentation can be ambiguous and can easily be implemented incorrectly, and we've seen that as well. So GNSS segment errors are there, and they're more common than you think, and we'll talk about that as well later on with some specific examples. And obviously, interference, RF interference is an issue. It's very easy to have a low-powered and compact small jammer, or even an out-of-band transmitter close by, which can cause issues with your signal. And then spoofing, well, that's where people will try to deliberately feed in a false signal to give you if you're talking about a positioning system, a false position, but for you all, it's to try and spoof the time, to change the time. And then it can be done. I'm going to show you some results we did back in 2016 to actually demonstrate that in a laboratory. So that can be done. And spoofing can happen accidentally too. It's been known to happen where people have, for example, created a repeater system and it's interfered with real systems. That's happened in Germany way back in 2010. So these are all vulnerabilities that are real, they're out there, all of these have happened and all of these can happen to a system. And the main question in terms of resilient PNT is, really, can you protect against all of these things, and what does that protection look like? It's not necessarily straightforward, but protection can be on a number of levels. And we'll talk about that in a little while. Now, when I started off in GNSS, I was involved very much in receiver testing and trying to mitigate and make receivers more resistant to jamming. And if I had £1 coin for every time someone asked me this question, how accurate and how good is a GPS receiver, I'd be very well off by now. It's a question everyone asks, and it's a very difficult question to answer, as we'll see, because the signals are coming down from space. And so we have to think about issues on the satellite. We have to think about the channel from the satellite to the ground and where that transmission channel lies and what's in it, if you like, and we'll talk about that in a minute. And then we have to think about what the environment is like close to the receiver. And then we have to think about what happens from the receiver's antenna to the host system. So, when you look at all of this, you can see that the accuracy of your receiver or how good it is depends on a lot of external things. So in fact, if you are a receiver developer or manufacturer, specifying the accuracy of your receiver can be a headache because it's dependent on external factors. And in fact, GPS accuracy today is It's outstandingly good, in fact, as these figures show. But, you know, the accuracy you get when you take the signal, the PNT information out of the receiver, can depend on a lot of other things. So this slide talks about geometry of the satellites, atmospheric conditions, receiver design. All of these things have an impact and more. I'll talk a bit more about that in a minute. You know, you've got other issues as well as those issues, which all apply to time and not just position. You've got to think about how that time is transferred, not just from GPS to the ground, but if you, for example, want to or place value on tracing it to UTC, how on earth does that work? Well, it's quite complicated. I mean, on the GPS satellites, we use GPS time, for example. That's what we use. But that doesn't synchronize to UTC on its own. For GPS specifically, and it's obviously different for different constellations, but talking about GPS, to if you like, have traceability from GPS time to UTC time, you have to figure out what the offset is between the satellite time and UTC. So for GPS, the UTC comes from the USNO, the Naval Office, Naval Observatory, in fact, and in Washington, DC. And what happened? Well, monitor the GPS time and figure out, US Naval Office, figure out what the offset is. And they have to steer the GPS clocks on the satellites to try and make them as accurate as possible to UTC. So it's really quite interesting. It's, if you like, if you're a systems engineer and you talk about a trace, it's not quite a trace. The US Naval Office steers GPS time to UTC to reduce that offset and get it as short as possible. And to a degree, it's not just about correcting errors. They have to predict some of the errors that come out, and then they measure on the ground and see how accurate they've been over the last few weeks or the last week or even the last day. And so it's a very complicated bit. But actually, the good news is that it's done extremely accurately. But again, more complicated. And if you start thinking about multi-constellation, that's between the different GNSS clocks and the different timescales on the satellites. So again, that's something else to worry about. Now, still talking about how good your GPS receiver. Let's just have a look at this diagram. It's a very simple diagram, actually. It looks very simple. But if we were to think about some of the mechanisms involved here, on the satellite, at the top, up here where the very poor drawings of satellites are, we'd have to think about, you know, how stable is the satellite clocks. We talked about the accuracy of the clock predictional models to GNSS time. So that accuracy of that offset is important. And as part of that, when they try to, make all of the corrections and predictions to keep that offset as small as possible, one of the things they have to think about is the accuracy of the prediction of the satellite orbital path. And also, as I kind of alluded to before, if you're using more than one constellation, does that help you or could it hinder you? Well, it obviously on the surface is going to help you in protecting yourself against some of the vulnerabilities, but the complexity can hinder you as well. Then the transmission channel, if you like, where we come down, the satellite signal has to go and be transmitted all the way down to the antenna array. And that means you've got transmission issues to think about, delays in the ionosphere. GPS signals are greatly affected by ionospheric or atmospheric phenomenon in the ionosphere. Delays through the troposphere, they're much smaller compared to the ionosphere, but you may have occasions where you have to think about it. And then once you've overcome all those issues, you've got to think about some of the issues near your site. how accurate is the phase center of your antenna? What about multipath buildings and structures near your GPS antenna? Are there any issues there? What about interference? Have you got any other sources of RF close to your antenna? Then you've got to think about the delays through the antenna system itself. Are they significant? What about delays between the antenna and the receiver through the antenna cable, if you like? You've got to think about the receiver and how the receiver processes the signal. And really, you're talking about a whole list of issues that you need to be on top of to get accurate time. And I've had a lot of experience of having to try and get measurements from live sky when you're testing just about to release a system. I've got a fly buzzing around at the moment. I'm just trying to clear it away from my camera. I think to show how complicated it is and to realize why simulation is an essential component of all this. When I did tests with systems under a live sky, I might do 100 hours of testing, but every time I changed a variable to do with the test, nature, as we've just seen through the list of issues around, is changing another, dozens of variables at the same time. So quite often 100 hours of live sky testing will only, if you're lucky, yield you about half an hour of reasonable test data. So it's an inefficient way of doing it. So simulation suddenly becomes very attractive. Now, having talked about all those issues and having talked about the fact that these signals from GNSS are weak, you can see that actually there are a few issues to iron out here if you rely on satellite constellations for your precision navigation and timing signals. And I think in the US, it was realized very early on that lots of critical national infrastructures, and it's the same here in the UK too, and the same in most countries, have actually become over-reliant on GPS timing with nothing else behind it. It just happened. I mean, PNT, when I started in it, it was in the military domain only, and there used to be a thing called selective availability on GPS signals, which meant that for civilian use, it wasn't as accurate as the military had their GPS signals. And that deliberately introduced inaccuracy meant that it wasn't really useful for many applications. But when that was taken away in 2001, when the commercial use, the civilian use of GPS exploded, people realized that this is a very cheap way to get precise time. I mean, there's no other comparable way. And so the use of PNT GPS is, it's become ubiquitous. It's in lots of systems, complicated systems. Quite often a full understanding of how that GPS PNT data is used. So dependencies on GPS are growing, and GNSS too. But GPS for timing specifically, the dependencies on GPS timing, well, it's huge. It's pretty much everywhere. And not only is our dependence on GPS time, which has got known vulnerabilities, not only has that dependence become huge, not only has it become ubiquitous, not only have we not necessarily done the systems engineering in a lot of places to understand the dangers of that sole source with its inherent vulnerabilities, but we're getting, as IT technology has experienced, we're starting to get increased frequency of the threats from different people. At the top, we've got unstructured. These are actually Sounds Institute groupings, but we can relate all of these to people who have carried out attacks, deliberate attacks against GPS, and maybe not quite deliberate attacks. So, for example, unstructured hackers, these are individuals who carry out an attack. Sometimes these can be unwitting people. So with GPS, a lot of companies now track activities using GPS and track activities of their employees. Well, if you're an employee, a small jammer that will jam the tracker in your vehicle, for example, if it was a delivery vehicle or something similar. And the issue with that is that although you think you're just jamming cab, you're actually probably jamming devices for a few hundred meters all round. So I know I did some work in the UK at the Satellite Applications Catapult up in Harwell in the UK, and we found tracking devices in vehicles and vans causing disruption to a receiver from up to 500 meters away, even though these were milliwatt jammers and devices. The structured hackers are probably the people who are doing these or carrying out these attacks more deliberately, trying to target something. And there have been 1 or 2 examples of that. There's organized crime, industrial espionage. Organized crime, for sure, we have lots of evidence that criminals routinely take GPS jammers with them nowadays on a lot of in a lot of occurrences of theft of vehicles, for example, and also other criminal activities. It's a routine thing now because people are quite often using GPS trackers to keep an idea, keep a tabs on location, and also using a jammer can also erase a location from cell phones as well. So there's more and more reason for people to use them, so they're around. And that means that if you've got a fixed timing antenna close by to any of these incidents, you're vulnerable. Obviously, insider threats, funded terrorist groups, but the main one that we've seen as well in the last few years emerging is nation states. South Korea has often experienced very powerful jamming attacks from North Korea, and we're seeing recently Russia, increased use of high-powered jamming around Ukraine, but it's also been going on in exercises in North Norway. And also, if we talk about nation states, I don't know if anyone's on from the US tonight, but sometimes in the US there have been military exercises in remote sites, because the US has a lot of space to have remote sites to go test jamming and spoofing, and sometimes those signals have affected commercial aviation, and so the whole threat landscape for PNT is growing, and it's growing at I would say a rapid pace, and I'll show you some real incidents a bit later on. So it's something we've got to worry about. You're probably going to come across one of these. I think the other thing is, certainly in the UK, we talk a lot about, having a systems of systems concept in society, and that is because it's needed. We've talked about it for a long time. It's because, GNSS is ubiquitous, and it means that it's often is transparent to the people who use it. The people who need your protection don't realize they need it. And the complex system dependencies mean that when things go wrong, there can be a lot of cascading impacts. So it's not just one thing going wrong, it's a whole chain of events caused by one tiny problem. And we see that more and more. So it's something to be aware of. And it's something that means that we have to be very vigilant, I'd say, as to what's going on in society and making sure that everyone has that protection. I'm going to talk about the US again, because the US has, has led in a lot of fields. Once again, I'm showing that Department of Homeland Security chart. But you know, one of the fathers of GPS in the US is a Dr. Bradford Parkinson, and he's said for a long time that we need to guarantee, or there's an obligation to provide assured PNT for all users. And his framework, if you like, is this protect, toughen, and augment framework. And if you like, it's got 3 distinct strands to it. It can be used anywhere. Just because it's you know, it's a US initiative doesn't mean that any of this work is only usable in one country. I'd say a lot of this work can be generalized and used internationally, because the problems are the same. And actually, one of the challenges to any of this standardization work, any of this education work, any of this guidance work, is to make sure that we cross boundaries and have something that works right around the world, not just in one country. And some of these principles are the same. You know, if you think about protect, toughen, and augment, the 3 strands there are protecting the radio spectrum, but it's also about you know, identifying and prosecuting or doing something to reduce the number of interferers. But it could also be, you know, protecting users through providing them with useful guidance. Other legislation, which might be to make sure that you use some sort of augmentation. The protection is a raft of soft measures that can be taken by any government in any country to help make sure the landscape is right. And it's also things that users can do. You know, if you are, you don't have to wait for government. So if you have you know, an operational handbook which people go to, then, you know, you should have something in there. If you use PNT, you should have something in there that explains how your business uses, say, precision time and from GPS, and what they should do if certain events happen. Even if it's not to do anything, at least it's there, and you're protecting people and they have to take. Then we have the toughen. The toughen is probably an interesting one, because there's a lot we can do to interferences, and also against deliberate interferences, and probably more than most people understand. I say that with a bit of hesitation, because I know there's a drive to augment and to have other sources of PNT because GPS is so vulnerable, but we shouldn't write it off either. There's a lot you can do to toughen the GPS receivers, which helps, and I'll show how that can help in a little while when I talk about the bits of resilience. But also, yes, you have to accept that Jeep-derived PNT data is a single source. So you need to do something about that. You know, single sources with a systems engineering hat on, you know, your single source isn't a good way of, for example, looking after your critical infrastructure for precision timing. So you need to think about additional sources, and that might even be just holdover, but it might be another PNT source perhaps. And those augmentation sources form the 3rd strand of protect, toughen, and augment. And I think they're great principles. I think you can transfer them anywhere. And I think we see that anywhere, you know, in the US. I mentioned before the P1952 standard for PNT user equipment. And that, I guess it would be fair to say, that standard started when the US started to look at what was needed to introduce resilient navigation and timing, or PNT conformance frameworks. And in the UK, we did something a little bit, well, quite similar actually. We had a thing called a Blackett review, which is an obscure name, a very critical scientific review. And that was about satellite-derived time and position and the study of critical dependencies. And although we didn't talk about the framework in quite the same way, if you were to, the problems we're facing are the same, and they're international problems. So I believe that, you know, it is possible to put frameworks in place that can help to improve things for all users all over the world. Now, I think I've been talking about resilience for a little while, but it's worth thinking about when we start thinking about what we might need for a standard and the sort of things we might do as to what this thing called resilience might mean. And there are lots of definitions around. And I think an interesting, without talking about specific definitions, and you'll find that there are lots of definitions around. If you join or talk to people who are working on the P1952 standard, they've collected a lot of the definitions, and they've caused a lot of debate, quite rightly so, because it's a difficult area. But if you like, resilience needs two components. It needs a component of resistance, and it needs a component of recovery. So, you know, resistance is where a receiver might detect your anomalies with the signal sources, or in other words, find or tell you that something is going wrong, or understand itself that something is going wrong, and can carry on operating so that normal operation can continue. Brackets, I've put in no disruption. But as we'll see, I'll touch on it in a bit. This is the sort of thing I could talk about for a whole hour on its own, because, you know, what do we mean by normal operation? That opens another interesting few few thoughts. And then recovery. And recovery really is how, you know, something gets through to your receiver, or something actually disrupts it. What happens to the system when the threat gets through? And so you can see that a combination of those two elements is really important, but how they're combined is important as well. For example, you can imagine a receiver that is very, very resistant to, say, jamming, but when a jammer does get through, the receiver can't recover. So what's more important to you? A system that is more resistant to jamming, so it's only, say, 1% of attacks that cause it disruption, or is it more important that you have something that always recovers, but maybe isn't as resistant to the jammer? It's an interesting trade-off. I'm not going to answer that right here, but what I'm going to show you is some tests we did with Calnex, in fact, in Spirent laboratories in 2016. And what we tried to do was, well, we didn't know it was possible. We were working in a small porter cabin at Spirent in Paynton in the southwest of England. And we did not know whether you could spoof a timing receiver. So we thought we would have a look and see whether we could. So we took a sample of a few timing receivers that were in use in the industry, and we tried with a simulator and some Calnex time measuring equipment to have a look and see whether we could actually spoof the receivers, and whether there'd be warnings or that meant that we wouldn't be able to spoof them. To our surprise, we spoofed them all, and we did actually get some warnings on one of the receivers, but it carried on taking the false timing data. We fed it. But I think the interesting thing is with these two plots is that, you know, we're saying, you know, what does resilience mean when you're spoofing a timing receiver? And you can see that in the top diagram, the black line is what we call a pseudo range ramp. So what we were trying to do is, by moving the, once we spoofed the receiver, we tried to move, if you like, the time of the receiver by playing around with the pseudo ranges. Now, there's a few things here. A lot of people talk about a thing called TRAIM, or timing RAIM. RAIM was receiver autonomous integrity monitoring, which is originally brought in for aviation, which is a dynamic safety of life critical application so the receivers can work out when if there's something wrong with the signals that we're providing to critical systems. Timing RAIM is just an extension of that, but with the assumption that the receiver is stationary. But one of the things that you might note about these lines is that actually the location would have remained the same all the time because we were able quite easily to spoof all of the signals. And so although the location would have remained the same and nothing unusual in the location of the timing receiver or the timing antenna would have been detected here, you can see that actually the time followed the ramp that we gave it. And we were trying to, we weren't sort of trying to get huge amounts of time offsets into we were just talking about 100 nanoseconds or so at a time, and so small distances, but we wanted to see if it was possible, and it was. So the top trace shows that actually when we were able to spoof the BPS output of the receiver that we were testing, it actually followed the ramp that we sent it. And it was challenging though, as the second device shows you, it was challenging to get repeatable results. And you can see that this particular receiver actually did try to give us a few warnings. We had some status reports, locked us in sync, but not GPS steered. Although having said that, although it gave us those warnings, it carried on outputting the data. So it wouldn't have actually saved you if you'd been using that in the system. But you can see there were some big peaks and big exceptions there. So that receiver wasn't happy. And although we just about spoofed it, it acted in a very strange manner. So we might not have, we might not have fully managed to confuse it. But the point is, if we're talking about what does resilience mean based on those two results, I'm not sure that I could give you a good answer because it's challenging to get those repeatable results. Even using a simulator, it shows you that of complexity, complex system behavior. So in other words, we have to think about a lot of considerations. We have to think about a lot of things to make resilient PNT work. How is it used in the application area? For you, it's your data centers. It's about constructing a use case, which tells you what the mission is, what are the objectives. It's not always easy to state. It sounds easy. You have to think about what the likely threats are too, because you don't really want to prioritize unlikely threats. You might want to consider them, but you need to think what the most likely ones are too. You need to think about relevant legislation and existing standards too, because if you were to develop your own standard, you don't want it to duplicate other standards or even to conflict with them. Dependent systems, data flow, and most importantly, and often forgotten, how do you measure the improvement that you have you've brought in? And that's often not done. So people don't actually think about how to measure that improvement. But I think that's critical because, if you're going to say that you've mitigated or you've achieved resilient PNT, have you really achieved it? What have you achieved? How have you measured it? It's really important, and it's important for standards to consider as well. Another piece to think about, something else that you'll hear about is harmful interference. What do you mean by harmful interference? And again, this is some data we measured in the lab. We were looking, there's one definition of harmful interference, which is quite widely used. The US Air Force have written a paper on it. ITU have used it in the past, a lot of important organizations, and it's called the interference protection criterion. And that is a 1 dB drop in carrier to noise ratio, which is the red circles on the top diagram show where we were measuring a 1 dB drop in carrier to noise ratio at certain RFI power levels. Now, you might notice that the carrier to noise ratio here, when the two receivers we were measuring, drops in two different places. Why is that? Well, strictly because in this case, it wasn't strictly a carrier to noise ratio. It was probably more signal to noise ratio from the receiver. In other words, there was some processing after the carrier to noise ratio drop, which is why it occurs in different places as the interference level or the signal power is ramped up. But the point is, you can see a 1 dB drop, and that 1 dB drop in the carrier to noise ratio is a really good way of saying that's harmful interference, because it turns out if you do the maths, which is fairly easy actually, you can show that a 1 dB drop in carrier to noise ratio equates to just about, I think it's 5.7, 6 dB increase in the noise floor, which, and that's a good metric to use because it saves you having to do what is happening underneath, which is where you start looking at what goes on inside the receiver. So some people will say, well, harmful interference is where the receiver starts to exhibit bad behavior. But the trouble is that can vary in behavior for each receiver. You can see the blue trace and the black trace there. Receivers responding to the same interference. I've also put error bars as well onto the horizontal position error. Look how different those two receivers are. For the receiver where the plot is in black ink, the interference may not even be all that harmful, even at a high power level at this particular band and this characteristic. So this would open up, a lot of problems to trying to get consistency. I think there are two approaches to achieving resilient PNT. One is that you use a systems consideration, and a colleague of mine, Mitch Narins, from Strategic Synergies is an advocate of the systems consideration, and that is that when you start thinking about how you implement something that will work, you must absolutely decide whether the equipment is resilient or not based on your required performance parameters and whether it meets those performance parameters. And if it doesn't, it's not resilient. If it does, well, there are two ways. It can be either meet the desired performance parameters as well as the minimum ones. It adds value to the user, or it might just be resilient. It might not meet the desired performance parameters, but it might meet the minimum ones. That's one way of doing it. It's also a very complicated way of doing it. If you've got lots of use cases and lots of different equipment, it can be quite complicated. I've tried to simplify this a little bit, just to say that, if we think about the systems considerations, then from my perspective as a GNSS person, I start to think about what's going on in the receiver. So I simplify that to, what are the observables that I can see in the receiver from those GNSS signals, and then based on the levels that I need, it's either resilient or it's not resilient. And that's what I look at. And I might make it a little bit more spicier by injecting some threats, hazard, and disruption into that cloud as well to see what happens when there are real problems. And also from a simulator, we can also change the satellite parameters as well. So this is how I start working it. And then another facet to all of this is the DHS resilience and resilient framework concept. And I think the easiest way or the best way to put this is that what you do there is you simplify the picture by defining resilience levels that the equipment can either conform to or not. And if you look at this resilience concept diagram from the DHS Science and Technology publication, you can see that up in the top left-hand corner, I've been talking about threats and testing against threats and how to do that. But you can simplify it a little bit by assuming that a lot of those threats and disruptions get through. And then really you're all about trying to protect a trusted core, which could be a trusted augmented time source. And if you do that, it's possible to set resilience levels. And the P90 is looking more at using resilience levels in a constructive way. And that's going to hopefully avoid a lot of the complexity of dealing with hundreds or thousands of individual threats on an individual basis. And so combining that with a good systems approach is likely to come up with a way of providing guidance and standards that could apply to a lot of people in a lot of use cases. I think quickly, just to go through some of the real world problems with the GPS weak number rollover before. This is something that happens. It's an epoch of it's a particular feature of GPS time, and it's caused by a 5-bit field for the GPS weak number. And when that rolls over on legacy equipment, there's a problem, obviously. And as that's every 19.7 years, when GPS was designed, it wasn't thought to be an issue. But lo and behold, it's been an issue. One of the biggest failures, in fact, was at the New York City wireless network, which crashed on the 8th of April 2019 because their system couldn't handle that weak number rollover when it happened. And what's worse with this is that it was a planned event. So everyone knew this rollover was coming. And so there was plenty of time to look and see if your system would have a problem. And also because people have implemented it in different ways, it's still going on now because you can implement it in a software way that means it's a sliding window. Other real events, well, we saw in 2015 a solar weather event, and I'm letting you know about this one because it was a particular timing issue. And it was a UK critical national infrastructure operator suffered broadcast outages. And actually the locations of those outages actually did quite a good job of following the path of this solar weather event, which I'll link to, as it tracked up across the UK. Another one was an internet box that was found in France to jam Galileo signals, and it affected the commercial operations of a company in France. So that was a timing issue. We see Northern Norway. The Finnmark police chief says there's not much they can do about it. It's a reminder that as reliance on GNSS grows, receivers must be protected against the effects of RF interference. They've been living with it there for a long time. And this is because of Russian jamming. It's an exercise, they're trying equipment out up there, but it's affecting them in Northern Norway and Finnmark. There was an issue in Belgrade recently where Belgrade marathon users reported distances measured incorrectly with hundreds of meters added to officially certified lengths. No one really knows what happened there yet, but that was obviously some sort of event. And one that's going to be published soon, and it's been mentioned recently in the US at the CGSIC, there was some sort of event at Denver International Airport, and it caused quite widespread problems to commercial aviation operations. We know that because pilots reported incidents, and it may well have been, affected people on the ground. There are at least 19 separate pilot reports that I've found, which are all related to the event and talk about various system failures and issues. And that was in January this year. So there's quite a few events there. I could list loads more. At the bottom of this slide, I've listed a whole host of issues that we've found. And today, we actually have a scenario pack for timing applications. And we can actually send you probably more information on that should you need it. But we split up the pack into some fundamental tests that look at baseline tests, leap year, the leap second, and the weak number rollover, which are events that have caused problems in the past, and things, performance tests, things like tracking sensitivity, multipath, autonomous integration, autonomous RAIN, autonomous integrity monitoring, I can never say it properly, and obscuration and multi-GNSS operability. So a lot of fundamentals there that you can start, that we have today, that you can start looking at with with a simulator to see what you have. The diagram on the bottom right-hand corner is actually showing a multipath simulation. Practical resilience assessment is important. This slide just tries to go through the sort of things you need to do. It's characterizing, understanding the mission. It's all about understanding your threats and your weaknesses. It's about thinking about the cybersecurity framework and integrating PNT issues into that, I think, is important. And it's about implementing a cost-effective mitigation strategy based on all of that. And if you can help bring in standards for data centers that will help you do that, then I think that's a really good thing to do. So I'd say, you know, consider your resilience from the start, understand what it means, understand your threat environment. It's complex and resilience can be heavily threat dependent, so you need to know it. You must know your system dependencies, and you need to know, you know, if GNSS is denied or disrupted today, how long, you know, can your system carry on providing adequate performance? Something you should know and know very well, and need to know if you need to extend it. And standards and guidance can be very beneficial, as can some sort of conformance assessment framework. I wouldn't necessarily do that in isolation. Definitely use systems as systems thinking, but, you know, definitely look at work that's ongoing. And again, it sounds like I'm plugging P1952. Perhaps I am, but it is a developing standard that's focused on GNSS user equipment, and with the concept of user levels of resilience, and also with, you know, some very good ideas about cyber resilience as well. It would be worth, I think it would be worth your time having a look at that and seeing either or whether you can do something off the back of the work that P1952 are doing. You definitely need to, you know, be aware of the other standards and make sure you don't tread on their toes or duplicate as well. So it's a complicated space, but in a nutshell, that's it for this talk. So thank you very much, and you can join my GNSS vulnerabilities group on LinkedIn, where we keep the discussion on jamming and spoofing events going. Thank you, and thank you for giving me the chance to speak to you.
Thank you, Guy. Thank you for that. And I would like to open the floor for questions from our team. Let's see if the folks on the call have any comments or questions.
Yeah, I have one, but if anyone else wants to go first, okay, I'd be happy with that. Okay, I'll go first then. Yeah, okay. I mean, I don't know how to say this. Okay, I've tried many times to like put this nicely when people have written about this topic on LinkedIn. It just feels a little bit like when people discuss this subject. Okay. Like firstly, I'm wondering, for instance, the threat at the moment, for instance, a lot of noise is being generated about, you know, we have an evolving conflict in the Western world with Russia. You know, what would happen if, you know, they started sort of disrupting that bit of the infrastructure, you know, and you know, I saw, you know, there's a special work group that sort of, you know, posted a picture where you see this laser shooting into space, hitting a GNSS satellite, and one of the solar collectors are sort of exploding, and that's literally science fiction, right? And I think it's something like, well, this is preposterous, right? And yes, you know, I mean, it just feels to me like this is a storm in a glass of water, which is going to be solved pretty quickly when new LEO constellation comes in, which are going to be much harder to jam. At the moment, with a bit of planning, if you have an antenna here and an antenna there, actually jamming a lot of like carrier grade antennas on a football field sized, you know, on a roof of a data center. If you look at somewhere like NY4, for instance, right? It's an enormous building. You have to literally fly over to jam it, and so on and so forth, sort of to make anything work. And even if you were able to do that, the maximum consequence of it is that you know, you have a grandmaster, it's going to go into holdover, and the odds are it's not going to last very long if somebody does something about it, right? So for me, it's like the worst case scenario is that if you could do this in a place where latency requirement is really extremely low, you know, maybe you could get a couple of codes that drop on 5G and they would immediately fall back to 4G. And I'm just like, I see a lot of vendors pushing this risk, but I have very few stories about actual outages that have occurred and real money that have been lost. It's like if I go outside my house, I can also be hit by an asteroid in my head. But if I multiply all of the probabilities together for the fact that this is going to happen, I just get like the expected cost of this risk is just tiny. I don't. Okay, this just sounds very negative, but what do you think about that view?
Well, yeah, it's always good to get this out there, isn't it? Well, you know, I actually take a very balanced approach to all this. I think, you know, if you have done the systems work correctly and put the right mitigations in place, then you make sure that your own risk is quite small. And maybe in your case, that's fine. You've done that, and if you've done that work and you've made your risk space small, that's good. Good, but it's like everything, that risk is scalable. Now, I'm not going to talk about people firing lasers like GNSS satellites, but I'll talk about a few things about just the satellite segment itself. Now, I think in 2015, while GPS were decommissioning a satellite, and it caused a timing exception of, I can't remember what it was. It might have been something like 15.7 milliseconds. I don't know. I'll have to check that. So don't quote me on that. But it caused a timing exception. Now, if you had a receiver there where the manufacturers had implemented the interface control document properly, you wouldn't have seen a problem. However, it was an ambiguous section of the ICD, and thousands of receivers did, and it caused issues in timing centers all around the world where, you know, there was not such an easy defense. And if you were using PNT from satellites on that day, and if your receiver complied with the interface control document for GPS, you'd have had a timing error. And it caused issues for a lot of people, including famously, because there was a report, the BBC in some places. So, you know, so the risk is there. And I say, you just have to deal with it. And you have to deal with it intelligently. So I'm a big believer, being a systems engineer, in using systems engineering to figure out what your risk is and to protect yourself, but make sure you're never relying on a single source. I mean, the thing is, you know, with my systems engineering hat on, my GNSS jamming and spoofing hat on, I'd say that, you know, the ubiquitousness of GNSS has meant that, you know, if I was designing a system to take precision time or precision navigation for a dynamic object, a dynamic system, I would, even not knowing about the threats, I would not rely on a single source of fixing data. I'd have something else. And you know, when you think about what GNSS is, it's a source of very convenient fixes for timing. It's from a precision time source. But, you know, really just relying on fixes from one system, how safe is that? Would I personally have a critical infrastructure system or a safety of life dependent system that was only dependent on one source? No, I would not. And that is before I know about the vulnerabilities. My systems engineering discipline would have said, yeah, you need to have something to make sure you're not dependent on a single source for any critical system. But yes, there are some people who are far too alarmist about these threats. Like I say, you have to understand your threat and your exposure and figure out from that whether you need to do anything about it. I don't know whether that helps.
Yeah, thank you. Yeah, yeah, I think that was a very English answer, and yes, a balanced view I think is good. Yeah, absolutely.
What would be a Danish answer?
I mean, okay. Firstly, as you know, I've now lived in this country for longer than I have in Denmark, but I think that's absolutely correct, right? I just think that GNSS is far more resilient than people give it credit for, right? There's multiple satellites in multiple constellations. More constellations are being launched, and if you want, you can have receivers in different places from multiple vendors, right? So I agree very much that, of course, you should not have a single point of failure anywhere. But those people that are saying, okay, we should start to, rely on, those old school systems again, where they build the radio mast, and you have to specify how far away you are and for it to work, like the one in mining, and we have one in the UK as well. Or we need to, build fiber infrastructure everywhere and so on, because we cannot trust what comes over the airways. Or the more sort of loopy stuff with the space lasers destroying the satellites and so on. I mean, so I agree. I just think at the moment there is a little bit too much full-scale panic in this discussion, and I think that guy's view is fair and balanced, and I agree with him.
Okay. Anand Ram, well, I think many of you know, wanted to convey this message before he dropped. And he said that we plan to work together with Spirent on getting some resiliency test methodologies circulated within the TAP members as part of the instrumentation and measurement workstream. So that's the workstream that Anand is working on with a bunch of other guys. So that's fun, and you can talk to Anand and hear more from Anand on next week when we have the summit. And Harold had a comment saying that the GPS timing error in 2016 was approximately 13 microseconds.
Yeah, that's it. There you go. Yeah, I had the year wrong by 1, and the error in microseconds was 13.7 or something like that. Yeah, brilliant. Thanks. I didn't have that in front of me. Yeah, and that was an interesting one because, thousands of receivers had a problem, but it was because the interface control document had been worded ambiguously that they had a problem.
And it's just to add to this comment. Do you hear me?
Yes, can hear you.
Yeah, I mean it's just by luck that timing error was 13 microseconds and not something much larger, I think.
Yeah, it was. Yeah, I think that's right. I seem to remember. I think I did read a report on what happened, and I think the data was flagged. There was an obscure flag that flagged the data as being out of date, and the receivers that had implemented the ICD properly correctly flagged that data as being out of date and didn't use it. But where receivers hadn't implemented the ICD properly, they didn't see the data as being out of date because they didn't consider that flag, and then they used it, and then they had the error.
Yeah, just to add one more comment to Lasse's question. Really, I think some of the issues with jamming, for instance, then you think, okay, so the clock or the GNSS discipline clock will enter into holdover, but we've done some tests with jamming, for instance, and we see that depending on what type of receiver one is using, the clock doesn't necessarily enter holdover in a very graceful manner. So you may during interference, the receiver may hold on to some very marginal solution which actually has large both position and timing errors, which may tend to steer the clock really off course until it enters holdover with really erroneous control parameters. So just trusting the holdover capability of the oscillator is really not good enough, I think.
Yeah, you know, you make a really interesting point, and I think, and it's a very valid one too. So I think you're right. I think it can cause a problem. I've heard of
I lost the sound. Yeah, from Guy. Guy, can you hear us?
you know, I've heard of similar issues, and
Guy,
I've seen one where
Guy, can you take
another
one
issue,
sentence?
and the system, the oscillator during jamming, and I've lost you, I think.
Yeah, we want you, Guy, to start your answer from the beginning as you were going on and off.
Oh, okay. Sorry. No, I think that was a very good point about the oscillator, and I think it is true of those systems, of those kinds of systems, and it's not just, you know, we're going to the oscillator. You know, I've seen issues with systems where, you know, reverting back from the holdover to the GNSS, it's quite complicated. How do you do that? You know, how is it possible to do that in a seamless and correct manner as well? So yes, you're quite right. It's a very good point you made.
And I'd like to thank you, Guy, for a very good presentation. I agree with many of the points on thinking resilience and multiple sources, really. Not just protecting the GNSS receivers, but actually a combination of sources to protect, toughen, and augment. Yeah. So I'm working in the National Timing Laboratory in Norway, and we are our side has been pushing the augmentation in ways, working on fiber-based timing distribution, but clearly that's it scales very poorly compared to taking precision timing from the sky. But a combination of technologies in a resilient way is certainly the way to go. And in Norway, 2 weeks ago, we actually had an outdoor over-the-air spoofing and jamming exercise with many participants, and I hope some of them will share what they saw with their systems. But at least we monitored some devices.
That'd be really interesting.
Yeah, I mean it is, and in some sense, doing simulations in the lab is efficient. You can test many scenarios, but actually gathering a number of actors in one place and submitting them to a number of scenarios is also useful, and in some sense efficient, because you can do things over the air that you cannot easily do in a lab. So
yeah.
Ahmed, do you want to ask anything?
If my audio goes through, so just wanted to ask Guy, like, what do you think, like, what the approach that we're taking with dual GNSS and then a Mac, and like especially now that we're trying to also standardize the design of the, I mean, either we're going to call it like time card or timekeeper or something. So we standardize that part, and we standardize most of these, you know, events, like basically when you come back from a holdover, from basically coming out of a holdover, and like all these other things, like you have multiple devices and one of them handing it off to the other one, and like compensating for the short-term stability difference that you have between the oscillators and so on. What do you think? I mean, let's break it in pieces. What do you think, first of all, like, let's say systems adopting dual GNSS as a reliability, and they can be like basically to improve reliability. You can have, like, again, different bands, different whatever.
Yeah, it's a difficult one, Ahmed. I mean, you know, the principles you talk about are all good principles. I mean, I would say, you know, it's the protect, toughen, and augment framework is a really good place to start. And you know, when you're talking about multi-constellations and multi-frequencies, that's part of toughening. But then, having said that's the good news of it. The bad news is that I've seen jammers that can jam on multi-band, and because most of the signals aren't high power, the jammer can still be quite compact and cause disruption to multi-frequency and multi-constellation. The good news, if you like, is that with GPS modernization, you know, with L5 coming along, which is intended for aviation, the L5 signal is a lot more powerful, and that's going to mean that you know, using multi-frequencies or even just within GPS and using L5, you know, is going to be, you know, good. And also, you know, by using multi-frequency, you eliminate the ionospheric problems as well. So there are advantages. But like I say, it's all part of, you know, considering it in that protect, toughen, and augment framework. But coming up with some sort of formal framework and ways to assess and go about, you know, at least going through the process of assessing and making your system more resilient and more reliable as well, and perform as it's supposed to. I think those are all very good steps on that. So it sounds to me as though you're going the right way.
Sure. And then those methods, you think, should we have them where should we place them basically in terms of standard? Would they fit, let's say, in let's say the standards that we're going to have for the time card, or do you think they better sit in the P1952?
No, that I can't answer, Ahmed. I think, you know, I think you all have and understand the use cases much better than me. I can only give you some sort of guidance from the GNSS point of view.
Yeah.
But I mean, all I would say is, you know, that it's up to you with your use cases to figure out the best way of implementing it in practice. I think there are a number of options open to you that I could see. And I think it depends on your use case and where you want
Sure.
to go with them.
Sure. Thank you, Guy.
Do you happen to know the origin of the expression trust but verify?
Yeah, it's because, yeah, we use that a lot because it's okay, you know, we're saying, well, you can trust GNSS as long as you check to make sure it's not being, you know, that it is it's in the ballpark solution, that no one is spoofing your system or it's unprotected. You should always make sure you've got some sort of check to make sure that what you're receiving is a GNSS signal and it's doing the right thing.
Okay,
Far too many people don't. You guys do, but far too many people don't. They just take the data as being true without thinking about it.
I understand. I googled it, and the Wikipedia says the origin of the phrase is obscure, but understood to be a paraphrase of Vladimir Lenin and Joseph Stalin.
Wow.
Maybe ominous.
Well, that is quite ominous, actually. I never bothered looking it up on Wiki.
That's creepy.
Yeah.
All right. Looks like we had a very fruitful event today.
And you're all welcome, you know, you've got my email on the slide presentation. You're welcome to send me questions afterwards if you want to email me.
Awesome.
Awesome. Thank you so much. Take care. I'm going to close the call.
Awesome. Okay. Bye, everyone.
Bye.
Thanks. Bye. My pleasure.